The last one that we were doing on the last video was this cyclohexene one. Is that going to be a chair conformation or not? Why or why not? And when I looked at that, I was thinking about it and thinking about it and thinking about it. Figured out maybe it comes out to something like half chair. Then I realized I could make it on the model. Didn't realize that at first. And so if we put a double bond in here for this cyclohexene, and it doesn't really come out to a chair. Now, also in real life and real sphere packing bottles, and running the Hartree-Fock calculations on software isn't going to be quite like this. But you can see that chair conformation pretty much disappears. It doesn't require to go like so, like it did before. So it's it's a little flatter. I forget how this goes, but I'm thinking if you put a double bond here and a double bond here, and you have a benzene ring, that's pretty much planar. So it gets less and less of a chair conformation the more as you put another one in there and a third one. Okay, so then we were doing all of these. This was kind of a challenge once you get, sometimes up through G, A through G, and you had to determine if it's identical compound, if it's a constitutional isomer, a stereoisomer, or a different conformation of the same compound. So if you come up with something different, feel free to let me know. But on 4.66a, so this is still page 186 and 187. Number 4.66a, I came up with that one was a constitutional isomer. And for B, the second one, I came up with the constitutional isomer. Again, let me know if you disagree on one of these. For C, I came up with that's the same thing. It's identical. For D, when you cross the page, I came up with that one is identical. Same thing. E, I came up with that was the same thing. It's identical. It's just flipped over like a pancake. F, I came up with the stereoisomer. G, I came up with stereoisomer. H, I came up with those two are stereoisomers. I came up with the constitutional isomer. J, I have identical. Well, now you might wonder about that one. So let me see if I can do that one quick. Probably can. Okay, got that one. So I'm looking at this one. Down this carbon, this is what I have. I need one more of those. Which one am I on, J? Oh, I need a couple more of those. I ended up having to cabbage some of these here. There, I think I have it. So off one carbon, I've got 2 methyl groups. Off another carbon, I've got 2 methyl groups, and we're looking down it this way. So all we're doing is, see, the front one would be, call this one the front one and this one the back one. The one on the left would look like so, and the one on the right would just look like so. I'm just calling these the same thing because this is free to rotate. So I'm calling that identical. It's not even stereo, it's just free to rotate. Okay, and then K, I have a stereoisomer. And L, I have a constitutional isomer. So let me know if you disagree with one of those, and I'll take another look at it. Let's go on. 4.67. One of those is, it says, consider the structure of cis 1,2-dimethylcyclopropane and trans 1,2-dimethylcyclopropane. Which compound would you expect to be more stable? I wouldn't expect this to make a whole lot of difference. I'm not going to try to make that because there would be a whole lot of strain on those bonds, and there'd be a whole lot of strain on my little plastic pieces here to make a cyclopropane on that. But I would expect the trans to have be a little bit more stable, because if you could draw that like so, if this was well, I guess these are CH3 groups. They're pretty much out of each other's way, really. And then back here you have a hydrogen up and down. Those are pretty much out of each other's way. There's not that much interference there because there's not much a bunch of other stuff in there like there is with the ring. But compared to here, I think they have it this way. There's even less interference between them. And so when I was looking at it down this way, when you make this molecule, these two are going to be eclipsed, and these two are, this hydrogen is going to be eclipsed with this one. This methane is going to be eclipsed. Methyl group is going to be eclipsed with that hydrogen. If you look at it this way, these two methyl groups are eclipsed. These two hydrogen atoms are eclipsed. If you look at it this way, you've got methyl with hydrogen eclipsed and methyl with hydrogen eclipsed. So with the trans, this eclipsing, if you go back to table 4.6 and you look at that, as these two eclipse, that's a 6 and a 6, gives you 12. And on the cis version, we've got an 11, an 11 for the methyl groups eclipsing, and a 4 for the hydrogen eclipsing, which is 15. So the trans is more stable, it's lower energy. Lower energy, more stable. Okay. And then for 4.68, the question is, if we compare the sizes of the halogens, we find that they increase as you go down the periodic table. They get bigger, but the barriers to rotation are about the same. And they're not that different. So why is that? Well, basically the reason is as you go down the table, electronegativity decreases. So going down the periodic table, the electronegativity goes down. Okay, and this is especially true for the halogens there in that family, because fluorine starts at 4 and the other ones go down quite a bit, down to kind of an average off the table. Okay, let's keep going here. That's drawing here. I don't know. Yeah, I probably better use this one because I'm not sure I can replicate that on 470. Okay, so for page 187, this one here, next to last one, consider the tetra substituted cyclohexane. That means there's 4 groups substituted. If you draw both chair conformations of this compound, and I started with the carbons, I labeled them 1, 2, 3, 4, 5. And the way I have the first one drawn, I got a hydroxide up, and then a carbon with a hydroxyl group. And that was the mistake I made back with my sucrose molecule. I had a bunch of OHs on there, and one of them was a methyl group with an OH on it. It was supposed to be. And then the third one was nothing on it, no group on it. The fourth one, the chlorine was down. The fifth one, this what would have been a propyl group was down, but I have substituted on it to hydroxyl. That was down, so that'd be axial. Okay, so this is all in its own way. I didn't make this one, but it would be all up in its own business. This is axial, it's interfering on the top. This is axial on the bottom, it's interfering. If you flip this up, put the hydroxide up here axial, and then you have that CH2OH here, out equatorial, going over 2 spots, you got a chlorine that's now axial, and then this group is equatorial. Well, you have an axial here and here, but that's not nearly as bad, I don't think, as all this mess in here axial. So I think this one is the more stable. This one I'm not sure I can draw again. It was hard to figure out, number 470. The cis one you can't, at first I thought maybe neither one of them you could, but there is one solution for the trans. Maybe I'll try to draw this. The cis one you can't, because if you try to rotate this one, this part down and the rest of that up, then that hydrogen is in the way. And you have the same thing over here. If you try to rotate this, flip this part up and then that tip down, this hydrogen is in the way. So that can't go anywhere. There is a solution to this one though. And I figured out how to draw it. If you take the left side of it and flip it up, we'll draw the right side the same. I'll show you how I did this. So you gotta kind of start your bow tie there and go back this way and then up. So those two are the same, and then this way and then this up. Now, if you flip it this way and make that part of your bow tie, how do I do that? So that there's my top, and there's this side, and then that is parallel to that one, supposed to be. It didn't come out very good. And then this side over here, and then this up like that. I didn't do it right. I did it right. No, I gotta take it off here. Okay, let's try it again. Let's try it again. All right, so in the book, it's this way. About like that one, and then this one over here, and then up off like so. Okay, now I gotta go off here. That's the mistake I made last time. So that is now, there's the top of my bow tie. Okay, and then I have another one up here like that. And in here, and like so. Okay, that's how that one looks with the hydrogen sticking out there, equatorial, and one sticking out here, equatorial. You can do that. Now, don't deceive yourself into thinking that, oh, I flipped that whole molecule up here. No, I didn't. Yeah, I did. How'd I do that? Okay, it can't be the cis. I know that. So it's the trans, and I must have drawn something wrong. I haven't figured out in my head. It just didn't draw right. Okay, I know the problem. You have to flip this one too. Okay, try my drawing one more time. I forgot to flip this one too. One more time. This is hard to do, especially when you can't draw good. All right. So first, let's draw this one. Now, I gotta flip this one. So it's gotta go this way. There we go. And this is gonna turn out right now. 4.70. And then this line over here. And then that one. Okay. Now, that's gonna put my bow tie on this one off of here. Okay, and then this one, and then this one, and then this one. With a hydrogen here, and a hydrogen here. So now, both flipped. This one flipped down, and that end flipped up. And then this one flipped the other way. That's what I got.